All right, let's learn about double replacement reactions. We're going to be looking at pages 158 and 159 in your notebook today. And you're also going to need a couple of other items in order to really be successful. And that's going to be a list of ion charges, which you can find on page 156 in your notebook. And you're also going to need a solubility table. I've linked one in your Schoology page. There's also some available online, and you can find some in the classroom. But you're going to need a solubility table, and the solubility table is going to allow us to predict some products. Okay, so one of the things that we did in class is we learned about what a solid precipitate is. Because we learned that in order for a double replacement reaction to happen, in the first place, things have to be aqueous, because the partners have to be able to ionize or split up. And so the metal and the nonmetal ionize or split up in water, and then when we mix two aqueous solutions together, we may or may not get something to form out of that. If everything remains aqueous, then nothing new forms and no reaction happens. And so we kind of practice that in class, and I'm just going to show you that here so you can see what the lab looks like. But if I take, this is NaCl, it's an aqueous solution, and I put a couple of drops there, nothing really is happening. And if I take another solution, this is barium nitrate, and I put a couple of drops in there, I still have a clear solution. There's nothing new that formed out of that. And so since nothing new formed, I know that no reaction happened. Here's another mixture that I can do. So I'm going to take a couple of drops of NaCl. I'm going to take a couple of drops of something called sodium chromate. I mix those two together, and again, although the solution's yellow, nothing new formed. Okay, let me move this because I'm going to show you an example of when a solid precipitate does form, but it looks a little better on the black table here. Okay, so, but if I take two reactants, so here's some sodium chromate, here's some barium chloride, and I mix them together, I want you to notice what happens when I mix those two together. You see that kind of milky white substance? That's a solid precipitate. So what that means is of the three reactions or mixtures that I just did, the first two did not exhibit any changes, so there's no reaction that happened. But that third mixture formed a solid precipitate, and so I know that the reaction actually happened and formed something new, and I would have to do some work associated with that. And so that's what we're going to learn about today in double replacement reactions. Now, a solubility table, when we look at a solubility table, I'm going to zoom in here real quick. We have the different partners in solubility. And so in this situation, I know that I was mixing together barium and chromate. And if I take barium and chromate and I mix together, I see that, yes, that was the solid precipitate that I formed between the two mixtures. But when I mixed together two compounds and I ended up with the partner sodium and chloride together give me aqueous, and so that partnership did not form something new. Okay, so here we go. Let's fill in our notes portion first, and then we'll go from there. A double replacement reaction only occurs if you get that solid precipitate, a liquid, or a gas. So something new has to form from the interaction of those freely moving ions in the water. Because those ions are freely moving, it does have to be aqueous solution. And again, that's because those partners have to break up to be able to potentially form new partnerships. But one of those new partnerships has to be a non-aqueous compound. Just as a reminder, we've been talking about it for weeks now, that we never place a metal with another metal when we're doing replacement reactions. Okay, so to look through the actual process, what we're going to do is we're going to write the charge above each ion. And then we're going to write down the metals first, and then switch their partners so they end up with a new nonmetal. We then look at those new compounds, those new products, and we check the solubility table to see what those new products' states of matter are going to be. If both of them are aqueous, then nothing new happened, and we just write no reaction and we're finished. Those are my favorite kind of reactions. But if at least one compound was not aqueous, if we get at least one solid, liquid, or a gas, then the reaction occurs and we have to keep working. So if it's both AQ, if it's AQ and AQ, no reaction happens. But if you get a solid, a liquid, or a gas for at least one of your products, then you're going to have a reaction happen. So if that does happen, you then write the charges above them and correct their ratios, balance the complete reaction, and write the state of matter. And then we're going to also learn about something called the net ionic equation. The net ionic equation is showing us who actually made that solid precipitate or liquid or gas. And we do that by crossing out whoever the spectator ions were. If you know what the word spectator is, you know that a spectator is someone who watches an event but doesn't actually actively participate. So whoever was aqueous, they're the spectator ions. And so we're going to cross out the aqueous product on both sides of that arrow, and that leaves us with who was actually involved in making that new product in water. All right, so let's look at our first example, and we're going to run through that list of things that we need to do. Okay, so the first thing that I'm going to do is I'm going to come in and I'm going to write the charges above each of those. And so I'm going to use a charge sheet to do that. I know that barium is +2, bromine is -1, lithium is +1, and fluorine is -1. Okay, and I also know that I am going to then switch. I'm going to keep my metals in place and I'm going to switch their partners. So now instead of, I'm going to write barium, but instead of barium being with bromide, now barium is going to be with fluorine. And then I'm going to write lithium, but instead of lithium being with fluorine, now lithium is going to be with bromine. Okay, now that I've done that, to save myself some work, I'm just going to go ahead and check on the solubility table what the solubilities of these are. So I have barium and fluorine, and so I'm going to grab a solubility table, and I'm going to find it. I'm going to find barium, I'm going to find fluorine, and I know that barium and fluorine make a solid. So I know that this reaction is going to occur because I have at least one non-aqueous product. Then I look up lithium and bromine, and lithium and bromine is aqueous. So I know that the lithium and the bromine are actually going to be my spectator ions because they're what remain aqueous in the reaction. Okay, so now that I do know that I'm going to have to complete this reaction, I'm going to go in and I'm going to keep writing my charges above my compounds. So barium was +2, F was -1, lithium was +1, and bromine was -1. Okay, so given that, I'm now going to rewrite my equation with the balanced ratios. So that's BA plus BR2 and LIF. Those compounds were already written for me, so those ratios were already balanced. But I notice here that I have a 2 and a 1. That means that I need 1 barium for every 2 fluorine. So that's BaF2. That was solid. And then the +1 and -1, they cancel out, so I just have a ratio of 1 to 1. So I have LaBr, and that is aqueous. Okay. If I go to balance it, I have 1 Ba, 1 Ba, 2 Brs. So I need 2 here and then 2 Lis. So 2 here, and then that balances out my reaction. Okay, so this is my kind of completed reaction. But I know that in reality, Li and Br didn't form anything. They didn't actually stick together because they remained aqueous. So I'm going to say Li and Br are my spectator ions. And so I'm going to cross out Li and I'm going to cross out Br because they were just spectators. So I'm going to write that down. They were my spectator ions because they were what remained aqueous as a product. And so now if I rewrite my equation with just what actually formed, I would see that Ba plus 2 Fs formed BaF2 as a solid. And that's the reaction. So this is what we call my net ionic reaction because it's just what actually formed the solid. My spectators are what remained aqueous. They cross off on both sides. Okay, so now let's look at example number 2. And I'm going to go ahead and tell you example number 2 is going to be a no reaction because I want you to be able to see that before we do some other practice problems. Okay, so I follow the same process. I'm going to start with charges. Al is +1, Br is -1, Ca is +2, and Cl is -1. So I'm going to keep my positives and then switch my negatives. So that's going to be Al that's now partnered with Cl, and then Ca who's now partnered with Br. Notice first things remained first things. Okay, now notice that those numbers, the subscripts, did not come over to the other side. Those subscripts are there because they balance the ratio, so we don't bring subscripts over. And we don't do the work on that until we know that we have to. So I'm going to look up my new product, which is aluminum and chlorine. So I find a chart, I look up aluminum, I look up chlorine, that's aqueous. So I know that the first product is aqueous. And then calcium and bromide is also aqueous. And so I've got an aqueous and an aqueous, which I know means that no reaction is going to happen. But one of the other reasons why is I know that this would make the Ca and Br a spectator and the Al and Cl a spectator, which means that everything is a spectator and so nothing happens. And so we just say no reaction for this one because they were both aqueous. Both aqueous means no reaction. Both aqueous products. Okay, and so that's how these work. I'm going to do a couple of the practice problems over on page 158 if you would like to see those worked out, but in terms of the lesson, this is it for the lesson. Okay, if we do look at those practice problems over on page 158, I find them to actually be a little bit easier because they're in word form, and I like the word form because I can just change the names and then do the work from there. So I have aluminum iodide and mercury 2 chloride, so that's going to leave me with aluminum chloride and mercury 2 iodide. Now, notice that when I wrote that in a straight line with the rest of the reaction. That's pretty important. If you start trying to curve it around, things start getting not so good. So please make sure that you abbreviate or you write small so that you can write it all the way across. Okay, so now that we found our new partners, let's see if our new partners actually make anything. So I need aluminum chloride, that's aqueous, and mercury. I don't have mercury on this side, so I'm going to flip it over. And I'm going to see I've got mercury and I've got iodide. Mercury, iodide, also aqueous. So I have an aqueous and an aqueous, and if I have aqueous and aqueous, I know that that's a no reaction. Okay, so my next one is silver nitrate. So I know that that is going to be silver now paired with phosphate and potassium now paired with nitrate. Notice again that I kept the first things first and I switched their partners. Okay, so I find silver phosphate on my list. Silver phosphate is solid, so I know I'm going to have to do the work. Let's just see how many solid products I get. And then potassium nitrate. So here's potassium. Go over to nitrate. Also, that's going to be aqueous. So that is going to be my spectator ion. Okay. So I'm going to go in and I'm going to write charges above everything. Now that's really important because I need to turn these names into formulas. So I need to write the charges above everything. Silver is 1. Nitrate is NO3. It's -1. That silver is Ag. Potassium is K. It's +1. Phosphate is PO4. It's -3. Ag is +1. PO4 is -3. K is +1. And NO3 is -1. Okay, so now that I have that, I'm going to go in and I'm going to correct any charge ratios. I see that's 1 to 1, so that's going to be fine. That's 1 to 3, which means I'm going to need 3 potassium in order to make that balanced ratio. 1 to 3, I'm going to need 3 silver. 1 to 1, that's balanced. Okay, so I have AgNO3 plus K3PO4 yields Ag3PO4 plus KNO3. Notice the only subscripts I have in here are the 3 here and the 3 here that were needed when I had to balance those ratios since they didn't cancel out. Okay, I'm going to add that this is a solid and this is aqueous. I know that my spectator ions are going to be my aqueous components, so that means K and NO3 are spectators. So K and NO3 are spectators, and that means that my final net ionic reaction is Ag plus, oh, hold on, I didn't balance it, sorry. So I need 1 Ag, I need 3 Ags, and that puts a 3 over here. Okay, so that gives me 3 Ags plus a PO4 to get Ag3PO4 as a solid. And that's my net ionic equation. Okay, so just to kind of review what I did before I do a couple of other practice problems, I wrote down the names of the compounds and switched their partners. I checked their solubility. If they were both aqueous, I couldn't move on. But since one of them was not aqueous, I was able to move on for this problem. So then I wrote down the compounds and their charges. When I go to write their formulas, I take into account their ratios. Since their ratios canceled, I didn't need to use any additional subscripts. But these ratios did not cancel, so I needed 3 potassium in order to balance out that -3 charge. So that's why I got the K3. So I finished that out. Once I did that, I balanced the reaction with mole coefficient, so I had the same numbers of atoms on each side. And then I kind of crossed out my spectator ions, or my product that remained aqueous. And so that was K and NO3, so I crossed out K and NO3, and that left me with a net ionic reaction of 3 silvers plus a PO4 to give me that solid precipitate of Ag3PO4. Okay, so I'm going to skip down and I'm going to work on I'll do number 5 and I'll do number 8. 5 and 8. Okay, so with number 5, I have ammonium chloride plus mercury 1 acetate. So when I go to switch those names, that's going to be ammonium acetate plus mercury 1 chloride. Okay, so now that I've switched the partners, I'm going to find ammonium acetate on my chart. So here's ammonium, here's acetate, that's aqueous. My next pairing is mercury and chloride. I only have mercury 2, so we're just going to, mercury 2 and mercury 1 act very similarly, so we're just going to assume that it's mercury 2, the same one. All right, mercury and chloride. Mercury and chloride is also aqueous, so I had aqueous and aqueous, which means no reaction. All right, I'm going to do, I actually kind of lied. I'm going to do number 6, and then I'm going to do number 8. All right, so with number 6, I have calcium nitrate and hydrochloric acid. Now, we see acid. If you look all the way at the bottom of the paper, I've told you what those acids are. I did that because we haven't learned how to name acids yet. We haven't done our acid unit. So anytime you see something that's acid, I'm going to tell you the name of it or tell you what that actually is, and that's H and then Cl. And so we're not going to worry about the name. We're just going to worry about the fact that it's H and Cl. So physically cross off the name, ignore the name, and use whatever the formula is that I give you. The first thing will be H, and then the other thing is the second part of that. Okay, so when we go to write this, we're going to have calcium, and now it's going to be with Cl. I'm not going to worry about the fact that it's chloride. I'm just going to write Cl. And then it's going to be hydrogen, and then its new partner is nitrate. Okay, so I need to find calcium and chloride. So I take my paper, find calcium, find chloride, that's aqueous, and then I have hydrogen and nitrate. Hydrogen and nitrate, also aqueous. So aqueous and aqueous, that's no reaction. Okay, looks like I'm going to do a couple of these in order to make sure that we get some practice with ones that actually work. All right, so I'm going to skip down and do number 8, and let's be hopeful for number 8. Number 8 is copper 2 hydroxide and acetic acid. I see acid, so I cross it out. I go down to the bottom and I say, okay, what does number 8 actually stand for? And that's H, and then C2H3. There's a typo there. There should be HC2H3O2. I don't know what happened there in that typo, but that should be acetic acid. H and then C2H3O2. Okay, so I am going to have copper with the C2, and then I'm going to have H with the hydroxide. So that's copper 2, and it's now with the C2H3O2. And then I have H and hydroxide. Okay, so I find the copper and the acid, the C2H3O2, which happens to be acetate. So I find copper and acetate. That's aqueous. So that's going to be a spectator ion. And then I have hydrogen and hydroxide. When you put hydrogen and hydroxide together, you get water. Well, water is not aqueous, it's water. And so you're going to actually have to continue to do this reaction. Okay, so since I know that, I'm going to go in and I'm going to write my charges. Copper is +2, it's Cu +2. Hydroxide is OH, it's -1. Hydrogen is +1, acetate is -1. Copper is Cu, it's +2. Acetate is -1. Hydrogen is +1, and hydroxide is OH, and it's -1. Okay, so now I'm going to rewrite my reaction, balancing any charges that need to be balanced. This is +2 and 1. That's going to require me to write it as Cu, and then OH2, because I'm going to need 2 of those to balance out the charge. Plus, I already know that this is HC2H3O2, yields. This is going to be Cu, and then I'm going to need 2 of these acetates in order to balance out the charge, right? 1 of these and now 2 of those. Plus, and then H is +1 and OH is -1. That's just HOH, or water. I then look and see I need 2 here, which means I need 2 here, which means I now have 2 of this and I have 2 of that, so it's a balanced reaction. I know that my aqueous components were the copper and the acetate, so I cross out the copper and the acetate, and I'm left with net ionic equation of OH2 plus 2 H's giving me 2HOH, which is the formation of water in a reaction between copper 2 hydroxide and acetic acid. Okay? All right, and that's how pretty much all of them are going to work. The only time we have to do any additional work is if we get something that is not both AQ and AQ. If that is the case, we go in and we write the charges, we balance the ratios to rewrite it, then we balance the entire equation for atoms, and then once we've done that, we cross out the spectator ions and we're left with our net ionic equation. All right, I hope this helped you learn how to write double replacement reactions.